Okay, so last time we started the topic of checking whether a given polynomial big F is, look at the theorem. It has coefficients from a finite field. The finite field is also given to you, and the polynomial is given to you in terms of coefficients and monomials. Degree is d, and we want to check. Ultimately, we want to find factors of F, but first for that we have to check whether it's reducible or irreducible. So we show that it is reducible if and only if one of these GCDs is not 1. Okay, we gave a proof of this, and based on that there is this straightforward algorithm that you go over all i's taking GCD with respect to this x variable of f with x to the q to the I minus x. Q is very large. Q is given to you, even if it is a prime, it may be a 100-bit or 1000-bit prime. So its value is actually 2 raised to 1000. So this x to the q computation is, or the degree of x to the q minus x polynomial is huge. It is something like 2 raised to 1000 degree. So you cannot store it if you wanted to store all the coefficients. But thankfully here the coefficients are mostly 0. It's only x to the q to the I minus x, so you just have to compute one monomial. And that you will do by repeated squaring. Mod f. So you only need its value modulo f because you only want to compute the GCD. So if you find some I such that the GCD is not 1, then you will output that f is reducible. Otherwise, if you have checked for all I, then you will deduce irreducibility. So this is essentially cubic time algorithm. So all the way down to bit operations, this is a very efficient, fast algorithm. In fact, this is the only algorithm you can think of for irreducibility testing. And this gives you more. So this actually gives you partial factorization of f. So in case your input polynomial has 2 different degree irreducible factors, they will be separated. Okay. So if you have a degree, if big F has a quadratic irreducible factor and has a cubic irreducible factor, then for I equal to 2, the quadratic will come out. Okay, so they will be separated. So you will actually get what is called equi-degree factorization. So because of this, we can assume. So from now on, we can assume that big F has any irreducible factor of big F has the same degree. So either big F itself is irreducible or it has many irreducible factors all of the same degree. This we can assume without loss of generality now, so to speak. Okay, because this algorithm is, you have a fast algorithm to get to this point. One more property we want, we can easily resolve is what if there is an irreducible factor whose square divides f. Okay, so that is called squareful case. So what if each square divides f? So that is called squareful f. And the opposite of this is square free. So if all the irreducible factors of f, they are distinct or they are co-prime, we call f to be square free. Otherwise we call f to be squareful. So for example, f equal to x square, this is squareful. On the other hand, x plus 1 times x plus 2 is, this is square free. Okay, so x plus 1 times x plus 2 is, the roots 1 and 2 will be distinct. Even mod 2 they will be distinct. While in the case of x square there are 2 roots but both are 0. Right, so squareful versus square free. this can we achieve square freeness is the question by a fast algorithm. So in the squareful case we can use the formal derivative. So what is derivative of a polynomial? So for fx sigma ai x to the I d degree, this has only one variable, so the derivative is denoted by dou x f. And what is that? Yeah, so the derivative in complex analysis is defined by some limits, etc., right? But what is the final result? The final result is that x to the I derivative is just I times x to the I minus 1, right? So that is a syntactic expression. So by passing all the analysis, we just define that to be derivative. Okay, so since over finite field we don't have analysis available, so we don't want to use limits, etc. We just say that this polynomial where the coefficient of x to the I minus 1 or so hence the coefficient of x to the I is I plus 1 times ai plus 1. Okay, so it is slightly shifted and it is scaled up by I. This polynomial is somehow related to f and will turn out to be useful. And this is also a polynomial in the same field. So when is this derivative 0? What does it mean if the derivative, this formal derivative of f vanishes absolutely? Sorry? F has what? Yeah, sure. If f is constant, then obviously derivative vanishes. That happens in analysis. But here you are over a finite field fq. Characteristic is p. So what are the other ways of derivative vanishing? Exactly. So and I will be a multiple of p means that the monomial is a pth power. So derivative vanishes if and only if f is some function of x to the p. And you have learned before that, okay, that this is slightly different for some g and h. Okay, so one side is clear. If f is a function of x to the p, when you apply the derivative operator, since every monomial p divides I, the derivative will vanish. So every coefficient there, this I equal to 0 to d. Sorry? Yeah, it's the same thing. I equal to 0 term will not contribute. It's in one to one, it is in bijection with the representation of f. So every I is a multiple of p and hence I times ai will vanish. Okay, so one side is clear, the other side is similar proof. So let's do that. So let us say the support is S. So none of these AIs are 0 to begin with, but when you differentiate, what you will get is I, AI, x to the I minus 1, and this suppose is 0. Okay, so we are looking at the forward direction. So we are assuming that the derivative is 0, which means that look at this part. So this ai was non-zero in fq, but I times ai is 0 in fq, which means that I is 0, but I is a number, so which means that p divides I. So you get that every I is divisible by p. Is that clear? So hence f automatically defines a g such that f is g of x to the p.
Can't it happen that every AI is divisible by P?
Sorry?
Can't it happen that every AI is divisible by P?
Yeah, but we are assuming that ai is non-zero. We are looking at the coefficients that actually appear. That is the definition of S. S is the support of F. So all these AIs by definition are non-zero. I mean, the only other case is when F is absolutely 0. But then obviously F is 0 is a function of x to the p. In all other cases, there will be this support S, and here I will be forced to be divisible by p. So that gives you the definition of G. So which is actually it is just this x to the p raised to I by p, and how do you get h? So you can define h to be this ai to the 1 by p. Okay, so for I in S. So clearly h raised to p will be equal to ai x to the I, which is then f. Now, so G clearly is a polynomial over fq. Where is h? Where are the coefficients of h? So which is the same question as where is ai to the 1 over p? Sorry? Yeah, so why, if a is in fq, why is a to the 1 over p also in fq? Yes, so you have to use those properties. That's a small exercise. So I think we are assuming q to be p raised to n. So then ai to the 1 over p is actually the same as ai to the p to the n minus 1, right? This is the Frobenius, this is coming from the Frobenius congruence or identity. So for every a to the p to the n, which is a to the q, is a. So in other words, a to the 1 by p is actually a to the p to the n minus 1, which obviously is in fq.
Unique a to the 1 by p.
Yes. It is unique. So a to the 1 by p is a root of y to the p minus a, right? Y to the p minus a, if it has a root, all of them are the same because of characteristic p. So that shows that h is actually in fqx. Okay, so we have defined g and h as required. Any questions? So we just showed that if the derivative of f vanishes, then f is actually a function of x to the p, a polynomial in x to the p, which is also a pth power. Okay, so derivative vanishes only for pth powers. In no other case can the derivative vanish. So the pth power is actually, yeah, let us delay that for a while. Let's look at the effect of square fullness next. So say h square divides f. Okay, f is square full. Then what can you say about the derivative? I want to make a statement about the derivative. If h square divides f, h will divide the derivative. Okay. So this is a very useful property computationally because this gives you immediately an algorithm to test square fullness or square freeness. Right. So if there is a irreducible factor whose square divides f, then how can you discover it? It will divide both f and the derivative. So you just take the GCD. Both of them, I mean, the derivative is very easy to compute, and then the GCD is easy to compute. So when you take the GCD, square fullness will be discovered. When you compute the derivative, you may see that you may get it to be 0, right? That may also happen. But if the derivative is 0, then you already know that f is a power of p. So that is also an evidence of square fullness. Right? So either you see the derivative 0, which means something very strong about f, or when you take the GCD of this non-zero derivative with f, you get something which also is a evidence of square fullness. So either way you learn something using these two lemmas.
But in the second case, we cannot calculate the factor, right? If
Derivative is 0?
yes.
No, then you calculate more. Then you have, then you know that f is actually power of p. So you can remove this extra p, and the degree reduces.
Yes.
You actually go to a much smaller case, and then you will study that recursively.
I think each polynomial is a power of p, and by Frobenius we can take the whole thing to the power.
Yeah, that's in the proof. This is something that you must have seen in school when you learn derivative operator. So let f be g times h square. F factorizes this way in fqx. So if you apply the derivative operator, how do you expand derivative of product? So there is this derivative product rule, right? So you first differentiate g, and then you differentiate h square. And you see that h divides this. So that's it. So this is just the product rule of derivative. So recall that you have seen in analysis that if you find a root of the derivative which is also a root of f, you find a common root of f and the derivative, right? So what is the speciality of this root? It's a repeated root. In other words, it has multiplicity at least 2, right? So this is what the lemma is saying also. But the lemma here is completely syntactic or algebraic. Okay, there is really no analysis in this. Okay. So now we can assume square freeness because you can use this algorithm, one step algorithm, with just outputs GCD of f with the derivative. So this algorithm works if f is squareful. The case of derivative being 0 also I should somehow capture here. Let me change this.
Output should be f divided by the GCD of f and derivative of.
If GCD of f with the derivative is non-trivial, okay, so let me capture whatever we have learned till now to do with derivative in these two steps. So the first step, you just check whether the derivative is 0. If it is 0, then you know that f is a pth power, and you can easily, I mean, you saw the definition of h before, f equal to h to the p. So you just have to output that h. Okay, this is a trivial computation. The other thing you can try is compute the GCD of f and its non-zero derivative. If it comes out to be non-1, then you are sure that this is a non-trivial factor, right? Because it cannot be, its degree cannot be equal to degree of f. Derivative has a degree 1 less, right? So GCD, either it has degree 0, which is equal to 1, or it has degree between 1 and d minus 1. So it's a non-trivial factor. So you output it. Okay, so one of these outputs will be successful as long as f was squareful. Okay, if f is square free, then both these steps will fail. Is that clear? So that is the computational content of whatever we discussed till now.
In the first step, we need to carry out the GCD again, right? If f to the power 1 by p and GCD of f, we have to find it out again too.
Sorry? You just output, just reduce f to the 1 by p. It's a factor of f.
Okay.
It's a repeated factor of f. It repeats p times.
Irreducible, we cannot.
No, there is no claim, there is no such claim. Success just means output a non-trivial factor, that's all. So after all this work, we are at this point. So now we can assume that f has co-prime equi-degree factorization. So when you look at the factorization of f into irreducibles, each of the irreducible has multiplicity 1. They are all distinct and in fact co-prime. They all have the same degree. Okay, so after the previous two algorithms, you get to this point.
Sir, the algorithm we used for irreducibility, didn't that also give us
Equi-degree.
it gave us equi-degree, and did it also give us co-prime as well? Because all the factors would be multiplicity 1.
Yes, so I think that there we were, you have to take GCD with x to the q to the I minus x many times, because it reduces 1 by 1.
No, my point was if you take it only 1, then you get each factor of multiplicity 1. And there's no need to take it multiple times then.
Yeah, that is true. So this probably is, yeah, this may be an extra step then. It's probably not needed. Yeah, just the first algorithm, if you take GCD, when you take GCD with x to the q to the I minus x, that already is a product of co-prime equi-degree irreducible. So you start getting these things separated out. That is true. So we can write f, I mean we don't know the factorization, but we have the promise that it looks like this.
The whole f was some g square exactly.
Sorry?
The whole f was exactly g square.
See, yeah, if it was h square, when you take GCD of h square with proper x to the q to the I minus x, you will get out h. So say f has k such factors, and fi is irreducible. In the finite, in this polynomial ring of degree, how much? They all have equal degree, and f has degree d, so it's d by k. Okay, so now we are in this setting, that so you can assume that whatever polynomial is given to you by either of these algorithms, when you use them judiciously, you will get to the point where f has k irreducible factors, each of degree d by k, and they are unknown. But k is known, right? Why is k known? How do you know how many factors there are?
We know the overall degree and we know the degree of each factor. So total number.
Yeah, how do you know the degree of each factor?
First algorithm and the second.
So when you take GCD with this x to the q to the whatever m minus x, right? So that m, that exponent m is the degree of irreducible factors. So you know the degree of fi, hence you know d by k, from which you know k. Yeah, so this is the setting. So any questions at this point? So this sequence of this sequence of algorithms is called pre-processing for factorization. Okay, this already needs some development, but it's merely pre-processing, because still you haven't really found a way to completely factorize. Okay, this is still a bad case. So at this point now we will develop algorithms in a different way to further factorize and ultimately completely factorize in polynomial time. So first algorithm in this area was due to Berlekamp. So Berlekamp's algorithm. This will not be the full solution, but it is still applied, it is still used in many real situations, also in practice. So yeah, so remember this blue part. From now on, we'll just implicitly assume this. Okay, without saying, we'll assume that input polynomial f is this, looks like this. So the idea here is factoring f can be seen as factoring the quotient ring. So this quotient algebra A is FQX. Mod f. And on this you have to understand this quotient algebra, apply Chinese remaindering. Right? What do you get? So by Chinese remaindering theorem, this algebra A And remember, we are assuming that blue assumption, which is that F is product of Fi's. So the quotient algebra factorizes as direct product of Fqx by one factor, which is Fi. Right. So this algebra it factorizes into these k, again, quotient algebras. And what can you say about this quotient algebra Fqx mod Fi? Sorry? Yeah, Fi is irreducible, so this is a field. And what type of a field? It's again a finite field. So this is Fq, Fi has degree d by k. So we'll call it Fq prime. Okay, so this A is nothing but k copies of the finite field Fq prime. Okay, that is that. So this structure is known, but what is unknown is the isomorphism. Okay, the structure is known because you know k and you know q prime. So you exactly know what the structure of the algebra is, but what is missing is this this Chinese remaindering isomorphism. That is not known, because well, if that was known, then you would have been able to recover Fi's, actual factors of F. Right. So this is the way we see factorization of F. We think of this as an unknown isomorphism. So RHS is known. But the isomorphism we want to find. Hence find Fi's. In fact, let me clarify this a bit more. So when I say structure, I mean this. So this last thing, direct product of Fq primes k many, this is the only thing which is known. Okay, the previous isomorphisms are not known. You don't know how to map Fq prime to that thing Fqx mod Fi, because you don't know Fi. Okay, so when I say RHS is known, it's only the last thing. So with the abstract finite field, you know the structure, but you don't know how it is being realized in the current input situation. That you have to find. Any questions at this point? So any ideas, how will you find, using this quotient algebra, how will you find a factor, find F1, F2 dot dot Fk? Okay, so the way, one more thing that we can deduce from this structure is any element G of A is a k tuple. A1 to Ak. Right, so you pick any element in this quotient ring Fqx mod F, let's call it G, and in this unknown isomorphism, this G Chinese remaindering will map to a k tuple. Each AI is in this finite field Fq prime. and this element Gx is the same as AI mod Fi. Okay, so this is again just invoking Chinese remaindering. So Chinese remaindering takes an element of the LHS A, let's call it G, and just looks at the remainder. So G mod F1, G mod F2, G mod Fk will give you these coordinates of the K tuple. Right, that is how the isomorphism was. But since we don't know Fi, we will never know AI. Right, we can only go, as we go over G in A, we know that these AIs exist, but right now we cannot compute them. But it is a strong property that they are in a finite field. Right, these are elements, unknown elements, AI in the finite field FQ prime. We will try to play with that. So the first property is, what if you take you focus on those possibilities of A1 to AK which are in FP. So basically just numbers 0 to P minus 1. Then what can you say about G? So what are the G's whose K tuples are just numbers? Elements 0 to P minus 1.
Constants.
No, that is a mistake. Yeah, no, G is not constant. G will still be, G is constant only when all the AIs are the same constant. Because a constant mod Fi will be the same constant, right? But as soon as you take A1, A2 different constants, like even if you take 0, 1, that does not correspond to a constant G. It's actually a non-constant G.
Product of linear factors.
No, so I want to make it specific. What can you say about G to the P? I just want this property. For these AIs as tuples, as coordinates in the tuple, what can you say about G to the P? It is same as G, right? So that's a very useful property. That is what Berlekamp algorithm is based on. So the reason for this is when you do Chinese remaindering, then you will basically be looking at AI to the P. AI to the P is A. So, and this is true for every coordinate. So if it is true for every coordinate, it's true for the whole tuple. So the whole tuple raised to P is equal to itself, which means that G is raised to P is equal to itself. Is that clear? And then use Chinese remaindering. Chinese remaindering theorem is an isomorphism. So when you get this relationship between AI to the P, or this tuple raised to P equal to itself, by isomorphism, the same thing is satisfied by G. Okay, and so for various reasons which may not be clear right now, but they will soon get clear, this is the congruence which we will work with. Okay, this G raised to P equal to G, we want to find a G first that satisfies this congruence. So how easy is it to find those G's? Well, G equal to 0 satisfies this. G equal to any constant satisfies this. So G constant, so finding them is trivial, but they will not be of any help to us. We actually want to find a non-constant G which satisfies this. Okay, and finding that is hard. You don't, at this point you don't know any non-constant G that will satisfy G to the P equal to G mod F, right? So that's the first question. That in fact will be the most important question. So what we'll do next will be solving that problem. So basically find non-constant g such that g to the p is g mod f. So can you find this? That is the algorithmic question. Now once we have found it, how will it help in factoring f? So I claim that if you find this g, then you factor f. How? So such a g gives a factor of f. So what you have is g raised to p minus g 0 mod f. Can you factorize g raised to p minus g? What is the factorization expression? Just some expression. So I claim that this is a factorization. So if you look at the product g minus 0, g minus 1, dot dot g minus p minus 1, right, for all the constants, if you take the differences and multiply, that is g to the p minus g. Right, this follows from the Frobenius identity. So x to the p minus x. It factorizes into product of x minus alpha. So there in x you substitute g, you get this. And yeah, so that identity does not even need mod f. Mod f is just hanging around for free. But now it will be of help. So what this means is that product of fi's divide product of g minus alpha. Which means what? So what if you take GCD of g minus alpha with f and try this for all alpha? Is there any hope of that factorizing f? So when will all those GCDs fail to factorize f? Sorry. No. Say f is no. Sure. But f is we are assuming that f is reducible. Otherwise, the irreducibility test would have already said irreducible. So we are in the case when f factorizes into at least two things. So f1 times f2. So think of the case f1 times f2, k is equal to 2. So f1 times f2 divides this product g minus alpha.
So either one should divide. If f1 should divide or f2 should divide. So
the bad case will be if both of them divide a single g minus alpha, right? So basically you try to take GCDs, try GCD of f with g minus alpha with respect to the x variable for all alpha. And if none of these factor f, then it means that so in some of the GCDs you are just getting 1 and in some other GCDs you are just getting f, right? You don't get anything between 1 and f. So the time when you get f, it means that f divides that g minus alpha.
Why is it possible to get F dividing G, isn't the degree of G less than the degree of F?
No promises were made.
No, but we're looking at it mod F anyway, right? So find non-constant G such that G to the power P is equivalent.
We are going mod F, yeah. So we can, so we can assume here, find non-constant G, and let's add that. Of degree between 1 and d minus 1, that we can add. So degree should not be 0, which means it should not be constant, and degree should not be d or more, because if it is, then you can reduce mod f and get down to d minus 1 or less. Yeah, okay, so with that assumption, yeah, that I think then takes care of it. So then now you see the simple proof. So clearly, since f divides the product, all the GCDs cannot be 1, right? Somewhere there has to be a non-1, but then that non-1 cannot be f, because the GCD will have degree less than d. So something will factor. Okay. So this implies that there exists an alpha where GCD has degree 1 to d minus 1. So for some alpha, GCD has to be non-trivial, and that factorizes f, right? So if you can find this non-constant G, limited degree 1 to d minus 1, then by this process you will be able to factor f. How much time will this process take? How many times are you computing GCD? P times, right? So this process is not the fastest one, because it takes at least P time, and P itself may be 1000 bits. So this itself may take 2 raised to 1000 steps. But the saving grace is that it is not dependent on Q. So when the characteristic is very small and the field is very large, which happens quite often in computer science, because P is 2 and the finite field is of size 2 raised to 1000. So in those cases you can use this idea. Okay, this is fast. So let's add the time here. In so P times GCD, and the GCD is degree d, so that's around linear, and there is a log Q. Okay, so this if you can find G, then on top of that, in O tilde PD log Q time, you can factorize F. Okay. So, yes.
I'm just a little confused. So these irreducible factors Fi's are over FQ.
Their coefficients are in FQ, yes.
FQ. Can't G be over FPX such a G? But if it is, then
What do you mean G in FPX?
I mean its coefficients are in FP.
Okay. Well, we have not said anything like that, but fine. So,
I mean, so,
it's not related to this slide. So till now we have only shown that if you find a G with that green congruence being satisfied, then you will factor
that
efficiently.
G will not be in FPX. Otherwise, how can
Sorry, how can?
the GCD then not real factor?
I'm not sure. F has coefficients in FQ. If you take GCD of two polynomials, one has FQ coefficients, other has FP coefficients, the result will be FQ coefficients. Okay. Yeah, so now we will try to finish this main part, which is how do you find this g, okay, of degree 1 to d minus 1, satisfying g raised to p equal to g mod f. Any ideas? And you are allowed time PD log q, so you have actually enough time to try to solve g raised to p equal to g for g. How do you do this? So this is a very special system, and unless you use that speciality, you can never solve it. Okay, so let's see the first property, which is that the solutions of this what is the property of the solution space? Is it a vector space? Over what? Over which field is this a vector space? Sorry? Yes, so it is not FQ, it's FP. So over this base field, this solution set is actually a vector space, because if you take, let's actually do that. So if you look at a solution G1 and a solution G2, and you take a combination of this C1, C2 in FP, what is this raised to P? So you know that P goes inside. And then you know that C1 to the P is, you need this to be C1, which is why we said FP. And G1 to the P, G to the P you have taken from the vector from the solution space. So this is C1 G1 plus C2 G2. Okay, this is the proof. So this solution set is actually a vector space over the base field, prime field. Which means that to find all the solutions, you just have to compute a basis, right? And so since the solution space is a linear object, this is a big development. So it's not a non-linear system that you have to solve. There is a lot of linearity in this system. So exactly how you will solve this is, again you will use this P exponent. How do I want to do this? Yeah, so now let us do everything over Fp, so that needs some more notation. So let the finite field Fq be modeled as Fpy mod Gy, big Gy. So let us pick the specific model of Fq, and now the little g, it's a polynomial in X of degree d minus 1, and the coefficients were supposed to be in Fq, so now they will be polynomials in Y.
What is D, sir?
D is the degree of F in all the discussions. So what is the degree of Y? That's n minus 1. So let us think of little g as bivariates. I goes from 0 to d minus 1. That's for x to the I. And then there are these coefficients in FQ, which again we need to expand as y polynomials. Which goes from 0 to n minus 1. With unknown Cij, but they are in FP. Okay, is that clear? So little g is the unknown solution we want to find, and now we are thinking of it, or we have actually expressed it as a bivariate, individual degree d and n, d minus 1 and n minus 1, and the coefficients are unknowns. They are numbers. They are 0 to p minus 1. Right. So now we want to find these Cij's. So let us do that. So what they have to satisfy is this whole thing raised to p has to be the same as itself. Mod f. Right, this is the system. Now, in terms of the unknown Cij, what do you think? Is this system a linear system or a non-linear system? Remember that non-linear systems are very hard to solve, if at all you can solve. Linear systems you can always solve. So what do you think? Is this linear or non-linear in terms of the unknowns, which are Cij's? These are the things you want to find. Sorry?
Linear.
Yeah, why? How do I see it as a linear system?
If we take any linear combination of the constants, when raised to the power p, it will distribute and these.
Yeah, so the p will go inside and it will become Cij to the p, but Cij to the p is Cij. Right, so the whole system is actually a linear system in C's. That's it. So the LHS is the same as the last expression, Cij times x to the pi y to the pj. So now if you look at this congruence, the second one, this congruence actually gives you a linear system in the unknowns, right? The dimensions are not very large, so you just solve this. So you solve this linear system, find a basis, that is your solution space of G. So you have actually found all the G's. And amongst all the G's, you just pick something that is non-constant. Okay, so that is the full Berlekamp algorithm.
If we can find the constant, then we are getting something which is congruent to 0 mod f. So that is becoming our basis, right?
Sorry, say that again.
If we can find out all the Cij's
Yes.
from these equations after solving this equation.
Yes.
So according to this equivalence, we are getting a polynomial is congruent to 0 mod f, right? If we
Take the difference.
yes.
Well, the difference gives you the linear system. You want to, linear system for C bar means that you want to come up with a matrix of constants times C bar vector is 0. It's just a matrix times a vector equal to 0, and then you want to find the vector. So you just apply a linear algebra solver or linear system solver on this. How to get the matrix of constants? You just have to compare, I mean, you reduce x to the p to the I to degree below d, and you reduce y to the p to the j to degree below n, and then you compare the monomials both sides. Those are two representations, but they have to be the same. When they are in reduced form, they have to be the same. So when you compare the monomials, you will get many constraints. But they are all linear constraints, so you solve the linear system.
But after computing the constants, how do we get the basis?
No, that is a question in linear algebra. That you refer to your high school or maybe BTech courses. So, but we'll do the time complexity analysis next time. Exactly how will you, well, or in all these steps overall, what is the time complexity? It is something like matrix multiplication exponent. Linear system solving is much like multiplying matrices. So you can use fast matrix multiplication. We'll do that analysis next time.